Hello everyone, welcome to this faculty development program on FPGA implementation of digital design with Verilog HDL. I am Dr. Geethashree A, Associate Professor, Department of ECE, VVCE, Mysore. I will be dealing with the combinational circuit design using Verilog HDL. The first program that I will be doing in this particular section is 2:4 decoder using the NAND gate. Now, the figure shows a 2:4 decoder which has 3 inputs I0, I1 and enable with 4 outputs Y3, Y2, Y1 and Y0. The slide also shows the truth table where E indicates enable input, I1 and I0 are the 2 inputs of a decoder, Y3, Y2, Y1, Y0 are the output. From the truth table, we can see that whenever the enable pin is high, the decoder will be active, and whenever the enable pin is low, irrespective of whatever the input will be there, the decoder will be inactive. So when your enable pin is high and I0 and I1 both are 0, 0, Y0 will be made 0 with Y1, Y2 and Y3 high. When I1 is 0 and I0 is equal to 1, Y1 will be made 0 with rest of the other outputs high. When I1 is 1 and I0 is 0, I2 will be made 0 and rest of the outputs will be high. And when both I1 and I0 are 1, I3 will be made 0 and rest of the output will be 1. Now when your enable input is 0 and whatever will be the input of I0 and I1, that is don't care, all your output, that is Y0, Y1, Y2 and Y3 will be high. Now this is the block diagram, block representation of 2:4 decoder and the corresponding truth table. Now we need to implement this 2:4 decoder using a NAND gate. So this is the circuit of a 2:4 decoder with a NAND gate. So I am using NAND gate, that is N1 and N2 as an inverter to get the complement of I1 and I0. And I'll be using 4 3-input NAND gates to realize a decoder. Now we'll see how to write the code for this 2:4 decoder in structural design. So the first thing is I'll be declaring the module. So module name will be, module is a keyword. The name of the module will be a decoder and the inputs are I1, I0, E and Y is your output. So I have 3 inputs and 1 output. Next, I'll be declaring I0, I1 and E as input and Y as output, which is a 4-bit array. So the declaration of array is in this way. I need to use a output identifier, okay, output keyword, square brackets, 3:0 and Y. Next, I'll be considering wire S0 and S1, these nodes, that is the complement of I0 and I1 to indicate complement of I0 and I1. Now I'll be writing the structural code for this. So I'll be using NAND gate. So NAND is a keyword for invoking a NAND gate. N1 is the name given to that NAND gate. The 2 inputs, whenever we are using an inbuilt gate, output will be defined first and inputs will be defined afterwards. So I need to map the output of N1 here. So this is the N1 gate. Output of N1 is S0 and input to this 2 input NAND gate is I0 and I0, such that your N1 will act as an inverter. Similarly, N2, your output will be S1 and both the inputs to the NAND gate will be I1 and I1. Then N3, your output is Y0 and input is S1, S0 with enable. It's a 3-input NAND gate. Then NAND 4, that is N4, output is Y of 2, input is S1, I0, E. Similarly, N5, output is Y of 1, input is I1, S0 E. N6 in output is Y of 3, I1, I0 and E are the inputs at the end with this end module. Now this is the code for a 2:4 decoder using a NAND gate. Here I am using the inbuilt NAND gate, where the inbuilt, whenever I am using an inbuilt NAND gate, I need to define the output first and then the inputs. Now after studying about the code of 2:4 decoder using NAND gate, I need to write the test bench for simulation. Test bench is a code where I'll be giving the specified input to check the output and verify the truth table. Now we'll move on to the test bench code. Now how do I write a test bench? To write a test bench, the first thing is I need to use the keyword module with a module name. So that I've given it as tb_v with semicolon. Here whenever we are writing the test bench, there is no requirement to declare inputs and outputs. Then whatever inputs that I have declared in the main program, those should be declared as registers. So I'll be declaring I0, I1 and E as registers. Then outputs should be declared as wire. So Y will be declared as a wire of 4, that is a vector of 4 bits. Then I'll be calling the main code decoder. Now this is decoder is the module name that I've given for a structured code of a decoder, and UUT is the instance name, that is unit under test, and open the brackets and map the registers and the wire that I have used in the test bench to the module's input and output, like dot I0 of this test bench will be mapped to I0 of the module decoder. Dot I1 of this test bench will be mapped to I1 of decoder module. Dot E of this test bench will be mapped to E of decoder module, and dot Y of this test bench will be mapped to Y output of the module. Now after calling the decoder or module under test or unit under test, the next thing is I need to give the initial values to the input. So for that I'll be using the keyword initial, then begin. So I'll be initializing I0, I1 and E to 0. Now after initializing the inputs, all the 3 input to 0, I'll give a delay of 10 units. So this is a runtime unit in your Verilog. So runtime unit is nothing but whatever will be the screen unit, that will be the runtime. That is, if the screen unit is nanoseconds, it will be initialized for 10 nanoseconds. If it is picoseconds, it will be initialized for picoseconds. Then I'll give the inputs, required inputs. That is the input that we have declared in the truth table. That is when I0, I1 is 0, 0 with enable 0 for 100 units. Then I0, I1 is 0, 0 when enable is 1. Then when I0, I1 is 0, 1 and when enable is 1. I0, I1 is 1, 0, enable with enable 1. I0, I1, 1, 1 with enable 1. So all these combinations will be maintained for 100 screen units. Then after this end, I have one begin here, so I need to end here, the end module. So this is the test bench of 2:4 decoder. Now I will be running the code and showing you the simulation output. So for that I'll be opening Xilinx. So after opening Xilinx, next I'll be going to file, open project. I've created already the project, so I'll just open that project. So the project that I've created is FDP. So I'll be opening that project. The project will be included here. Now to this created project, I need to add the decoder program. I've already typed the decoder program, so I'll just be adding the source. So I'll click on add source, and after clicking on add source, I'll be including, or I'll be selecting decoder.v. So this is my decoder.v code that I have already typed. Now this is the actual structured design of a decoder.v. Now I need to include the test bench for running this code. Again, I'll go to add source and I've saved the test bench by name tb.v, that is testbench.v. I'll be including this. Okay, now when I include this testbench.v, this testbench.v internally is calling your decoder.v. So if I open this testbench.v, I'll be having a decoder unit under test which will be called in this test bench. Now to run this, here I need to go to behavioral simulation, then click on this plus symbol, your Xilinx ISC tool. Okay, so click on the test bench and check syntax. Check whether the syntax is proper. After the syntax has been cleared, then go to simulate behavioral mode. And you can read the input. Now I'll be setting the markers to read the inputs. Now this is my first combination. So I will be checking all the 5 cases here. Now, so this is the first case. Okay, now here my input I0 is 0, I1 is 0 and enable is also 0. So all my outputs will be 1. Now when my input is I0 is 0, I1 is 1 and enable is high, Y0 is high. Similarly, when my I0 is 0, I1 is 1 and enable is 1, my Y2 is 0. Similarly, the next one, the next combination, when I0 is 1, I1 is 0 and enable is high, my Y3 is 0. And the last combination is when I0 is 1, I1 is 1 and enable is also 1, my Y3 is 0. Now this is the simulation output of a. Now we'll move on with the next program, 8:3 encoder without priority behavioral modeling. Now this shows the block diagram of 8:3 encoder where I have 8 inputs, I0, I1, I2, I3, I4, I5, I6, I7 with enable as the input. I have 3 outputs, Y2, Y1 and Y0. So totally I'll be having 9 inputs and 3 outputs. The truth table of 8:3 encoder without priority is being displayed here. When enable is 0, irrespective of whatever the input is there from I0 to I7, Y0, Y1 and Y2, all the 3 outputs will be 0. Now when your enable is high, your encoder will be active. When your enable is low, your encoder will be inactive. So when your enable is high, encoder will be active, and if I7, I6, I5, I4, I3, I2, I1 are 0 and I0 is high, then Y0, Y1, Y2 will be 0. Similarly, the next combination is when I1 is 1 and rest of the other inputs are 0, your Y0 will be high and Y1, Y2 will be 0. Similarly, the next combination, when your I2 is high with rest of the other inputs is 0, Y1 will be I, Y2 and Y0 will be 0. That is, when your I2 will be high, your output will be 2, decimal 2. Similarly, when I3 is high, your output in decimal will be 3. When I4 is high, your output in decimal will be 4, that is 100. When your I5 is high, your output will be 5, that is 101. When your I6 is high and rest of the other inputs are 0, your output will be 6, that is 110. And when your I7 is high and rest of the inputs are 0, your output will be decimal 7, that is 111. Now, this is the truth table of a 8:3 encoder without priority. Now, writing the code for this 8:3 encoder without priority, I'll be starting with the module, keyword module, and the module name is N823, and my inputs are enable, I and Y. Now, I'll be declaring the inputs, input E and input I, which is a array of 7 elements. Then output is Y, array of 3 elements. The output, as I'm using Y as in a behavioral logic, that is inside a case statement, it is necessary that Y has to be declared as a register. So this Y, I'll be declaring it as output as well as register. Then always at E, I. That is, always at E, I indicates that whenever an event takes place on enable and your input pins, this behavioral logic or the behavioral code should be executed. Begin, always at E, I. Begin, if enable is equal to 1, begin, case of I, I'll be using the case statement. It's an 8-bit input. When it is 0, 0, 0, 0, 0, 0, 0, 1, Y will be 0, binary 0, 0, 0. Similarly, when it is 0, 0, 0, 0, 0, 0, 1, 0, Y will be 0, 0, 1. When your input is 0, 0, 0, 0, 0, 1, 0, 0, your Y output will be 0, 1, 0. Similarly, when it is 0, 0, 0, 0, 1, 0, 0, 0, Y will be 0, 1, 1. When it is 0, 0, 0, 1 followed by 4 zeros, your output will be 1, 0, 0. When it is 0, 0, 1 followed by 5 zeros, your output will be 1, 0, 1. When it is 0, 1 followed by 6 zeros, your output will be 1, 1, 0. And when it is 1 followed by 7 zeros, your output will be 1, 1, 1. End case, end, else. I have a if statement here. If enable is equal to 1, case statement will be executed. If enable is equal to 0, your Y output will be 0, 0, 0. This end will end the if statement, and finally end model. Now this is the behavioral model of a 8:3 encoder without priority using case statement. Now moving on with the test bench of this. So as I've told you, module keyword, your test bench name, and there is no input and output declaration in the test bench. The test bench name will be terminated with semicolon. Then all your inputs will be declared as register, that is register E, register I, then output as wire. Then call your module, encoder module, EN823, unit under test is the instantiation name, and map your inputs of the test bench with the module inputs. Initial begin, give the initial values, that is E is equal to 0, I is equal to 0 for 100 screen period. Then give the combinations here. E is equal to 0, I is equal to 0, E is equal to 1, I is equal to 1, E is equal to 1, I is equal to 2, E is equal to 1, I is equal to 4, E is equal to 1, I is equal to 8, E is equal to 1, I is equal to 16, E is equal to 1, I is equal to 32, E is equal to 1, I is equal to 64, E is equal to 1, I is equal to 128, end module. So this is the test bench of 8:3 encoder without priority. Now we'll execute the code and check the output. Now I will be closing the previous code here and I will be adding the test bench. So if I add the test bench, the module will also get added because the test bench will be calling the module. Now a question mark has occurred here. So now I need to add the module once again here. So I'll be again going here, add source, the module, okay. Now the test bench and module both have been added. So I'll just open the code. So this is the test bench code and this is your module. Now I'll be checking the syntax. Okay. Again check the syntax of the module. Now click on the test bench module and run the simulation. And this is the code. So I'll be using the marker to check the outputs. Starting with the first combination. Okay, when my enable is low and input is 0, my output will be 0. Next, when my enable is high and input is 0, my output will be 0. Now the next one, next combination. Now when my enable is high and my input is 0 0, that is 2, my output is 1, 0 0 1. Now when next, when enable is high and my input I2 is made high, output is 2. So you can either keep it in binary or decimal. Okay. Then when my input is 8, my output is 3. When my input is 16, output is 4. When my input is 32, output is 5. Input is 64, output is 6. It continues in this way. So this is the output of a 8:3 encoder without priority. Okay, now we'll move on with the next code, that is 8:3 encoder without priority. So I'll be closing this window, simulation window and minimizing my Xilinx. My next code is 8:3 encoder with priority. The block representation of 8:3 encoder with priority is similar to the 8:3 encoder without priority. I'll be having 9 inputs, that is 8 inputs from I0 to I7 and 1 enable input with 3 output. There is only the variation in the truth table. So I'll be using don't care as the input. Now when enable is equal to 0 and all my inputs are don't care, my output will be 0, 0, 0. When enable is high and only I0 is high and rest of the other inputs are don't care, my output will be 0, 0. When my input I1 is high and I0 is 0 with rest of the input being don't care, my output will be 0, 0, 1. Similarly, when my input I2 is high with I1, I0 0, 0 and rest of the other input don't care, my output will be 0, 1, 0. So it continues in this way. Okay, now using this truth table, I need to write a behavioral code for 8:3 encoder with priority. Okay. Now we look at the code of 8:3 encoder with priority. Now the difference between this code and the previous code without priority is the usage of case X statement. Now in the previous code, in place of this case X of I, we had used case I. So the only difference between that code that is without priority and with priority is here in place of case of I, I'll be using case X of I because don't care condition has to be identified. So the first case is don't care followed by 1. My output will be 0, 0, 0. Then 6 don't care followed by 1, 0. Output is 0, 1. Then 5 don't care followed by 1, 0, 0. Output will be 2. 4 don't care followed by 1, 0, 0. Output will be 3. 3 don't care followed by 1 followed by 4 zeros. Output will be 4. Then 2 don't care followed by 1 and 5 zeros. The output will be 5. 1 don't care followed by 1 with 6 zeros. Output will be 6. And finally 1 followed by 7 zeros. Output will be 7. End case, end. If enable is equal to 0, y will be equal to 0, 0. End mode. Now we'll go through the test bench of 8:3 encoder with priority. The definitions are same. Module, I'll be defining the module. I'll give a name to the test bench of the module. The inputs will be defined as registers. Output will be defined as Y. And I'll be calling the module, that is encoder 8:3 with priority. And I'll be mapping the inputs of the test bench with the inputs of the module. Then initial values, E will be made 0 and I will be made 0 for 100 screen units. Then I'll be giving the inputs. When E is equal to 0, I is equal to 0. E is equal to 0, I is equal to 1. E is equal to 1, I is equal to, E is equal to 1, I is equal to 1. E is equal to 1, I is equal to 6. Then E is equal to 1, I is equal to 17. E is equal to 1, I is equal to 8. E is equal to 1, I is equal to 16. E is equal to 1, I is equal to 33. E is equal to 1, I is equal to 64. E is equal to 1, I is equal to 128. And end module. Now we'll move on. We'll see the execution of 8:3 encoder with priority. Now for that I will be opening the project. It is FDP is my project. I'm Now after opening the project, I have the previous code here, so I'll just remove this code first. Okay, now add source, and I will be including test bench of priority encoder. Okay, now I need to add the source code. Add source. So I need to add both my test bench as well as the module. So I'll be opening my test bench and module. Now first I'll be checking the syntax of the module, then check the syntax of test bench. So after that, simulate your behavioral. So this is your output. I'll be using the marker to explain the outputs. Okay, my first input is E is 0, I is 0, output is 0. My second input is E is 0, I is 1, even then your output is 0. Then the next input is E is 1, I is 1. My output will be 0. Then E is 1 and input is 6. So when E is 1 and input is 6, my output will be, I'll change this to binary. We can see that I have two ones here. That is, this is I0, I1, I2. I1 and I2 both are ones. So it will take the priority of LSB. So my output will be high. Then moving on with the next input, that is this means 17. So in 17 you can see I0 is 1, I4 is 1. So when as I0 is 1, my output is 0. Similarly, in the next input, I have I3 1, so my output is 3. The next input I have I4 1, output is 4. Similarly, in the next input I have 0 0 1 0 0 0 0 1, so my output is 0. So here I6 is 1, so output is 6. So it continues in this way. So this is the execution of 8:3 encoder with priority. The next code is 8:1 multiplexer using if statement. So 8:1 in 8:1 multiplexers, I have 8 input lines, that is from I0 to I7, and 3 select line S0, S1, S0, and 1 output Y. The truth table is being shown here. When your select lines S0, S1, S2 are 0, 0, 0, then I0 channel will be selected. When it is 0, 0, 1, I1 will be selected. When it is 0, 1, 0, I2 will be selected. When it is 0, 1, 1, I3 will be selected. When it is 1, 0, 0, I4 will be selected. When it is 1, 0, 1, I5 will be selected. And when it is 1, 1, 0, I6 will be selected. And when it is 1, 1, 1, I7 will be selected. Now this is the truth table and block diagram of a 8:1 mux. So we know that we have 7 inputs, that is I input, and 3 select lines, that is S input and Y output. Now we'll be defining the module. Now module mux 8:1 is the name of the module. I have S input, that is your select lines, I input and Y as output. So I'll be defining input is a 3-bit array. So S 2:0. Similarly, I input is an 8-bit array. So 7:0, 7-bit array. Then output Y. So as it is a behavioral description, output will also be declared as register. Then always set I, S whenever there is an activity in I and S begin. Then if S is equal to 0, 0, 0, if the select line is 0, Y is equal to I of 0. Else if S is equal to 0, 0, 0, 0, 1, Y is equal to I of 1. Else if S is equal to 0, 1, 0, Y is equal to I of 2. Else if S is equal to 0, 1, 1, Y is equal to I of 3. Else if S is equal to 1, 0, 0, Y is equal to I of 4. Else if S is equal to 1, 0, 1, Y is equal to I of 5. Else if S is equal to 1, 1, 0, Y is equal to I of 6. Else if S is equal to 1, 1, 1, Y is equal to I of 7. End module. Now this was a 8:1 multiplexer code. Now we'll move on with the test bench. So test bench module mux 8:1 underscore TV underscore V. Then I'll be defining all the inputs as register, that is S and I will be defined as register, and output Y will be defined as wire. Then I'll be invoking the multiplexer module. I'll be mapping the variables of the test bench with the variables of input and outputs of your module. Then initial begin. I'll be setting the initial values for S and I. S is equal to 0 and I is equal to 0 for 100 screen units. Then I'll be giving the test input. When S is 0, I will be equal to 0, 0, 0, 0, 0, 1. So this is the input, channel input. When S is equal to 1, output I is equal to 1. When S is equal to 0, I is equal to 4. When S is equal to 3, I is equal to 0, 0, 0, 0, 1, 1, 0. I'll be giving all the test inputs like this. Then end module. So now we'll see the execution of this particular code. Now I'll be adding the test bench and the code here. Go to add source. So you can see here I have both my test bench and my module. Okay, now I'll be clicking on the module, mux module, check syntax. Okay, now click on the test bench, check syntax. Now after checking, now click on the test bench and simulate behavioral model. So I'll be using the marker to explain. My first input is I is equal to 0 and S is equal to 0. So Y will be equal to 0. My second test input is S is equal to 0 and I is equal to 1. So if I convert this into binary, my S is equal to 0, 0. So I naught is 1. So my output is 1 here. My next input S is equal to 1, S is equal to 1, and here as S is equal to 1, this is I0, I1 is 0, so my output is 0. Now the next input, S is equal to 2. So this is I0, I1, I2. I2 is 1, so my output is high. Similarly, when S is equal to 3, this is I0, I1, I2, I3. So I3 is 1, so output is high. The next test input is S is equal to 4. So I0, I1, I2, I3, I4 is 0, so output is 0. Similarly, when S is equal to 5, I0, I1, I2, I3, I4, I5. So I5 is higher, so output is high. The next test input is when it is 6. When it is 6, even I6 is high, so my output is high. So this shows the simulation of 8:1 mux. The next code is 4-bit binary to gray converter. Now this is the circuit diagram of a binary to gray converter. So it's a 4-bit binary to gray converter. So I have B as input, that is B0, B1, B2, B3, and G0, G1, G2, G3 as output. So from the figure we can see that B3 is equal to G3 and G2 is XOR operation of B3 and B2. G1 is XOR operation of B2 and B1, and G0 is XOR operation of B1 and B0. So with respect to this particular circuit, the truth table has been constructed. When binary input is 0, gray input is 0. When binary input is 1, gray input is 1. When binary input is 2, gray input is 3. When the binary input is 3, gray input will be 2. When the binary input is 4, gray input is 6. When the binary input is 5, gray input is 7, and it continues. Now we'll be writing the behavioral code for this. So to start with, I'll be defining the module B to G, that is binary to gray. I have B as input and G as output. So input, it's a 4-bit vector. Output is a gray 4-bit vector, that is G. As I'm writing a behavioral model, I'll be defining the output as a register. So register G, which is 4-bit. Always set B, begin, case of B. So define the variable. When it is 0, input is binary input is 0, output is 0. When it is 1, output is 1. 2, output is 3. 3, output is 2. 4, output is 6. 5, output is 7. Similarly, when the binary input is 6, gray output is 5. Binary input is 7, output is 4. 8, 12, 9, 13, 10, 15, 11, 14, 12, 10, 13, 11, 14, 9, 15, 8. Now this was the code for binary to gray converter. Next we'll move on with the test bench. So I have a default value also, where default value is don't care, end case, end module. Now we'll move on with the test bench. Now writing a test bench module B to G underscore TV underscore B. I'll be defining the input as register and output as wire. Then I'll be calling the module and I'll be mapping the variables of test bench with the inputs and output of the module. Initially I'll be making the B input is 0 for 100 screen seconds. Then 1, B is equal to 0 for 100 screen second, B is equal to 1 for 100 screen second, then 2, then 3, 4, 5, 6, 7, 8, 9, 10. And end module. We'll see the execution of binary to gray converter. So I'll be including the files here. So I'll be including the test bench first. Okay, then include the module. And check whether both have been included here. Now check syntax for the module. Okay, Then open the test bench, click on the test bench and check syntax. Now I have to do that. After checking the syntax of both test bench and the module, now click on the test bench and run the code, simulate behavioral model. So you can see when my input is 0, output is 0, input is 1, output is 1, input is 2, output is 3, input is 3, output is 2, when input is 4, output is 6, when input is 5, output is 7, when input is 6, output is 5, when input is 7, output is 4, when input is 8, output is 12. Now this is the simulation of binary to gray code converter. So this completes the combination design logic in Verilog. Thank you.